Now, Chui, welcome to PostGIS Day.
Thank you, Paul. It's good to see
Good
you
to see
here.
you again. So I've been describing you as one of the members of the Victoria Geospatial Mafia, and I'd like to clarify that. You're like, why am I saying this? Because yeah, I've known you for a very long time. I believe we met over 20 years ago. And at the time, you were working for Mark Sondheim, who's the source and root of so much of the geospatial work we do here in Victoria. And you were working on the JTS project, if I'm not mistaken. And
Yes,
contributing to that foundational piece of geospatial work as well. So it's great to still be in touch after all these years.
thank you, Paul. And you are the one showed me the first command how to use PostGIS back in 2001.
Oh, really?
I still remember so clearly. You were the first line of command, and
Okay.
yeah, and many years working with Martin on JTS.
Yeah. All right. So you're going to be talking to us today about Polygon edge mapping. You taking control of the screen and go ahead.
Okay, can you see my screen?
Yeah.
All right, I will start. Yeah, in this presentation, I will briefly explain how PostGIS helps us to implement a technical solution to simplify map compilation and data integration without complex edge matching, maybe in a way without edge matching at all. And also how PostGIS and open source software and open standards advance our data management and geospatial web services. I'd like to provide some background on what we do and the direction we are taking on the open source software, perhaps more relevant to managers and solution architects in the audience. The British Columbia Geological Survey, it's in the province of BC, one of the provinces in Canada. The survey is the oldest scientific agency in the province. We collect and deliver geological and mineral resource data to support mining and land use planning. And so BC has amazing geology and rich mineral endowment. Here is a map showing the major exploration projects and producing mines. And here are some dollar numbers. As you can see, it's a multi-billion in the mine produced and also multi-billion in terms of even expenditure in looking for mineral, what we call the mineral exploration. So very significant. And I should say the mining is a important economic component in the province. And as a matter of just this week, we have a dedicated Ministry of Mining and Critical Minerals. So behind the scene, we maintain public geoscience, and the survey operates 40 plus databases and applications. And we build most of these systems over the decade by our staff geologists. And most of them, if not all of them, they are pretty much siloed system at the moment. And many of them still on legacy or even obsolete technologies. So this diagram is just to show you there's a intrinsic interconnection between our databases and also huge dependency when we update, when we query our data. So for example, mineral deposits are controlled by bedrock geology. So to update our mineral inventory, we need access to digital geology. We need access to exploration, mineral exploration and mining activities in the province. So this is why we put a business case together to build a geoscience spatial data infrastructure to essentially migrate and modernize our databases and applications to a common platform with consistent and coherent standards and architecture. And most importantly, perhaps with fewer technologies to maintain. So right now we have a few dozens, which just simply unable to keep up with that. And I'd like to share you with the good news. Our business case has been approved with capital funding, and the PostGIS is the key technology to implement. So we do have a few projects ongoing right now to modernize a few systems. And again, pretty much migrating from Fox Pro, from SQL Server, from Microsoft Access, essentially to PostgreSQL and PostGIS. So I will now just switch the gear, turning on to something, the specific topic I'm talking about today, which is the BC digital geology. So here's the color rendering of what we call digital geology. We define it as the authoritative data source containing all the details. This is not on a specific scale. It's all the details we can put our hands on. And digitally seamless coverage. And most importantly, a database we can update, and it's also analytical ready. So BC is one of the first jurisdictions with such a massive digital compilation on the bedrock geology, completed in the mid 1990s to support all kinds of applications such as mineral potential modeling and interoperable data sharing. So there's a few challenges to maintain this database, essentially to update. The first challenge is to handle boundaries shared by multiple feature types, polygonal and linear features. Just to want to clarify, bedrock is three-dimensional. Our digital geology currently only capture the superficial expression of rocks and structures as 2D or 2.5D. Just for convenience, I will use the term, polygonal, aerial, or linear features, and just for the convenience. So on the top of this diagram is a complete map with bedrock units and mineralization and faults, structures, sample locations, you name it. Now, typically in the GIS, we maintain our data on multiple layers. Usually start with geometric data type, and then just go on to feature types. So in our case here, we have the polygons at the bottom, mineralization as a polygon, and then faults, line work, sample locations as points. Now, those shared boundaries and using polygons is really causing a lot of troubles. In a typical scenario, in most jurisdictions, I think still something common practice is we crop a area, basically using the map sheet to crop an area with polygons and then go ahead to update. As you can imagine, this will cause all kinds of problems at the edge when you do the data integration. Essentially lots of work in the edge matching. So I would just a bit of a animation here. I don't know if that would work. You crop this out, and years later you bring it back. And we have gone through many iterations along the edge, all kinds of problems. Plus, on this example, you're going to find out using this kind of like a map sheet based scenario, we are going to introduce what we call like a data boundaries. Essentially crossing the data boundary, you're going to find different levels of details. And so digitally, it's complete coverage, but on the data wise, you're going to find discontinuity and disjoints at the map boundary. And so I will, yes, here just show you some specific examples in the actual data. And it's just a summary. So share the boundaries, and when you integrate, all kinds of work, time consuming, and also topological errors introduced during the map integration. And also how you can handle different levels of details, and a polygon constantly getting subdivided. And when you want to generate a product, you might have to amalgamate, merge a bunch of polygons. And also from the defined finished data product, how you're going to trace it back to their data source. So again, this is really my benefit for working with Martin Davis, Paul, and yourself, and also the process developing JTS and PostGIS. I was kind of inspired with a simple solution. Let's just drop polygons. Let's just look at a bunch of line work. Let's bring this one into PostGIS and see what happens. So it's a very, very simple data model. I put a name here called a geospatial frame data model. And essentially what I'm looking at here essentially is the frame as a picture frame. When you add the picture, you finish the product. So as you see what's on the left-hand side, right-hand side here. I wasn't planning to have this slide, but after Paul mentioned the topology without topology, whatever. So in the back end, when we look at the data source, we're not looking at topology. To me, the topology is the end product. How big you want to build your kitchen in the house, and what's the relationship between the red and the yellow Lego pieces? There's no topology in the back end. And it's only when you build the final product, let's have the topology, okay, more explicit as you want it. So to implement this thing, we are obviously using PostGIS. And just on the right-hand side, it's just like a simple UML diagram to explain. Again, I know this presentation will be on YouTube, so people can look at the details later, and also some publication we have online. Now, before I get into the another huge benefit is essentially on the integration without edge matching. Before I get into the detail, I'd like to explain a few nautical terms. The first one is the anchor line, essentially the line between the anchors, essentially the red line here. And then the anchor points, obviously just anchor. And road line, essentially the green line between the boat and the anchor. And the revision representing the boat representing the data we want to update, can drift to some extent. The line work can drift to some extent, but not at the anchor point. Now, using this terminology, so when we need to update an area, they are representing the dotted red line, we will be using this kind of anchoring concept, essentially to accept all the features in entirety intersected. We're going to tag them, and then we're going to apply the concepts we just mentioned for the outermost boundary. We'll tag them anchor lines, and at the joints, anchor points, and then anything else inside, either something for revision or the green line for road line. So we will give this package line work and then centroids for a geologist to update. And years later, this is what happening. So years later, they bring back the data. We could care less about the polygon. We're going to drop it, and we're going to drop their anchor lines as well. So back in the database. So before we getting ready to update our database, in the corporate database on the right-hand side, we're going to retire the old one, and then we're going to bring in the updated GFD centroids and the line work and bring them in. So the only thing is happening here, we just need to snap the road line, end of the road line, to the anchor points. And then that's then the story. And then we use extensively, we're using database views and the materials views essentially to finish the end product, which is not part of the GFD data source. Now, just like a cartoon to describe what I mean here. So before we check out, the road lines is locked to the anchor point. During the compilation and updating, the road line could drift away from the anchor point in the provincial database. The integration process essentially brings everything back here. Here's just a diagram to show the entire process. Started with step 1, checkout, and that's what we do. And the step 2, field mapping, field survey and the compilation, step 3, those will be done by our mapping geologists. And step 4, that's where we do the validation, only the line work and the sand choice before we integrate. So just getting back here, the map creation side, using database views, there's all kinds of actions we could happen, and then we could build a product with all the details, or with the details, whatever the details we want, lesser details, and filter, like even simplify the geometry. So this it's something we built in-house, and a prototype which has been in the operation in the last 12 years. Yes. So I just want to bring things back to home. It's using PostGIS, all kinds of, not only updating our data, but also providing data products as map or as download, but also to support our geospatial web services and interoperable data sharing, like we have the data on One Geology. So just for the One Geology side, why bring up something to the One Geology? This is again, the data and the services, they are compliant to the OGC standards, like a geoscience markup language, but also WMS, and also WFS. And again, using PostGIS in the backend, it make our life so much easier to map our data schema to the OGC standard schema, and also mapping, match our vocabulary, our terms to the standard terms. So in summary, we used PostGIS to implement a very simple data model to simplify the map compilation and to integrate new data to our system without complex edge matching. And it's also provide lots of potential benefits, like the linking to the data source from our end products. And also briefly, I mentioned that the system really, it is going to be, well, it's not going to be, it is the key system component in our SDI we are building right now. Obviously, many other benefits, a community like the one we have here, and I don't have to mention the cost effectiveness. Again, I know some people might be looking for some more detailed stuff, scripts. I've seen a lot of SQL statements from Martin's talk. So here, it's just a really simple one. The only takeaway is basically the beauty is using SQL statement. It doesn't have to be something really complex. As a geologist, I can put up essentially a single pass producing 2 different buffers. And these are the buffers we're using to basically select the features we want to update, and also the features we want to tag as anchor line, road line, or whatever. Fairly simple to do. Now, 2 different database views. The first one, a database view to simplify the line work without actually touching the line work in the GFD data source. So it happens only in the memory. And we can build another materialized view, essentially using the regular database view to form polygons, filter the features we don't want here, like the alteration, we want to drop them, and then create a new map. Again, only in the new map, we're talking about like a topology, not in the backend data source. Again, you can, another things we have to did, I cannot show the entire script here, essentially building the trigger to essentially tracking the version, tracking audit, like what happened to our data during the validation, during compilation, during the whatever. If I found something wrong, I'm going to fix it, but I don't want to fix that without leaving a record, a track of record. So just extending a little bit more, our benefit from the open source software for geospatial. So this, our front end, the map place is the interface, access all the databases in the back end. And it's built by ourselves using map guide open source, open layers, and GeoServer, and obviously PostGIS in the back end as the database. One thing I want to mention here, I don't know if how many people are using this one. I know, Paul, thank you very much. I know you did a lot of great work. on the foreign data wrapper. So I want to claim we are perhaps one of the largest user of the foreign data wrapper, because for our map place, it's not just like geological data, minerals. It's everything relevant to mining. So like a topographic, aquifer, you name it. So we use foreign data wrapper, essentially bringing every external databases, data sets we need, we want it, and the industry, our clients need it. Again, even this one, I can, there's a lot of details here. I don't think we're going to get into that. Again, thanks to PostGIS, it's a real database in the backend. Everything on the map place too is not a canned or static. It is a live database in the backend, which really allows us to run all kinds like a query, spatial, non-spatial. Here is an example to generate a geological like legend. Even in a typical GIS, it's not easy to generate a geological legend. And here, thanks to the database, and also the open source software, we were able to do this one automatically. And again, some spatial overlay to create a buffer, select a bunch of things, and using the whatever been selected, we can generate summary reports, and whatever is selected can be downloaded as KML as well. And I just want to wrap up my talk as a really big thank you to Martin, to Paul, and to Elizabeth for the opportunity to speak here, but also in general to open source community. This really allows us to do so much what otherwise we just can't imagine. So everything I highlighted here in yellow, either it's a open source component or something compliant to the OGC open standards. And yeah, that's pretty much what I have here. Thank you very much.
Thank you so much, Yao. Great presentation, and I love that data model. I loved it since you first explained it to me. It's a wonderful piece of jujitsu to make what appears to be an impossible problem very tractable. We got some questions from the audience. This one's one that I was going to ask. What tools and technology do you use for data editing, and what tools do you use for visualization and analytics? Are these in-house tools?
We are using QGIS as much as we can. And also traditionally, this is going back 20 plus years, the BC Geological Survey is perhaps one of the largest group using something called a manifold system. It is a GIS, and but has a incredible SQL interface. So essentially in the front end visualization, so even the map, the rendering I show you, manifold build a theme like in XML and store in PostgreSQL database. So that same theme, whoever hit that table, you're going to see whatever I see. If I am the one controlling the theme, you're going to see everything whatever I have defined, which is not only incredibly fast, it's incredibly fast. I know QGIS can do that, create some kind of trick, but it's kind of little bit slow. This manifold is incredibly fast, and then the code in the XML is really, really simple. So essentially myself, I've been using manifold way back in the early 2000, and still that's my default tool I'm using. But its backend is PostgreSQL, PostGIS. Any front end, anything else could work. For me, it's more convenience. I found it so easy in manifold.
Question from Warren Rowe. Great presentation. Is it fair to say that ST-SNAP is one of the keys to this process?
Yes, the snap. Again, we talked with Martin way back, and even during the road matching, even the snap, could it be a simple? Could it be warping? Could it be like proportional, warp the entire road line? Again, there's so many different options, tools out there. It's almost like at your disposal to do that. But in our case, because the drifting, our data in typical is 1 to 50,000 scale, could be even 1 to 250,000. So even you move like the end point by 5 meters, you're not going to see it. But
Right.
anybody concerned about like this will change your topology, whatever. There's all kinds of things you can do. The warping, shifting by an angle, whatever. Again, it's a really simple process in SQL.
You mentioned off to the side that you gave the data to the geologist to work on, and then they would come back years later. Years?
Yes, because depends. Minimum 1 year, right? Because the geologist going to the field, taking the sample. Some of the samples get analyzed, like the sample for isotope dating, like getting the age. It could take a significant amount of time. And also an area really truly trying to understand the geology. Let's say someone mapped this year, and then they could be going back next year. And years later, you got some new data. They could revisit either the site, or could be getting the data from industry, from academic, from whatever. Our map, I hate to say it's a dynamic. The map is never static. A unit get divided, subdivided. So it's not we had large area, like the Bowser Basin and the Southern Nicola Arc. It's a take like 10 years. Obviously, you get a bits and pieces coming back, but finally in 10 years, we really get a good handle on what's happening. We have a massive finale like compilation. So a couple of years, it's very common. 5 years, it happens. 10 years, significant, it happens. So imagine the data being taken out, multiple like a round trip being transformed to UTM, to Albers, to Lambert, to Las Longs, whatever. When you do this 100 times, because we do have collaboration with universities, Geological Survey of Canada, even with the US Geological Survey. So you never know the data being taken away. They do whatever they do, coming back. So essentially, we finally assembling, drifting. We like to think drift away, for 20 meters, not a big deal because we are not mapping out that kind of detail. But the drifting, it happens. It happens all the time. I wish I could have a talk explaining this kind of drifting. It's killing us, right? In terms, again, going back to topology, how you're going to control the topology when when the fundamental geometry kept like drifting, and when our units, the bedrock units kept like subdivide, merge. I want to combining the late Jurassic to the early Jurassic. I want to take out the middle Jurassic to a separate unit, you name it. So the line work is never static. Anyway, so we're dealing with something fairly, it's scientifically, I want to say controlled. It's scientifically evidence-based process. So we are on their mercy. You got a new data. We got to do something. Okay, let's do it, right?
Yeah. Amazing. So when you first started doing this, I seem to recall that you had to hide your database under your desk and not tell anybody it was Postgres. Because everybody
Absolutely,
not allowed to do that. So things have changed.
Yes, you are absolutely correct. 15, 17 years ago, open source was not it's a dirty word. And I really like to thank Oliver because finally the government listened. So 5, 6 years ago, now it became the other way around. You want to build something new? Why not using open source? Do you have any reasons not to use open source? So the tide really changed beyond how we started.
Well, thank you very much for all your work, and thanks for sharing everything today. It's a wonderful talk.
Thank you very much. Thank you, Paul. Thank you, Martin, and then the open source community. Also, really want to thank you, Elizabeth, helping, coordinating, taking some of the anxieties from me technically on the thing. And also thanks to Crunch Data for providing this opportunity. Thank you.